Hello, welcome to Open Source Community Health, Analytical Metrics, and their corresponding narratives. My name is Kevin Lombard. I'm from the University of Nebraska at Omaha. Today I'm presenting on behalf of myself, Sean Goggins from the University of Missouri, and Matt German-Prey from the University of Nebraska at Omaha. Open source software is a key component of our digital infrastructure. So this image is from a webcomic by Randall Monroe. I think it's really funny, but it's also very true, and it illustrates how open source project health is incredibly important to software ecosystems. So one unhealthy project can cause the entire stack to fall. So because of this, everyone involved in open source software wants to have a clearer understanding of the health and sustainability of their projects. Studies of open source health are spread across many research communities and domains, and they have explored community health through concepts such as open source success, sustainability, survivability, risk, and software quality. We define open source community health as a project's ability to continue to produce quality software. So prior work defines open source health in a myriad of ways. And each approach aims to make representations of open source health efficient through the collection, aggregation, and analysis of trace data from repositories, issue trackers, and other traces of work and communication. Our analysis of this literature surfaces a number of discrete activity metrics aimed at different aspects of open source health, including scale, project culture, process quality, product quality, contextualized risk, license risk, corporatization, and access to resources. So trace data are the building blocks for nearly all measures of open source health. This makes the collection analysis of data related to software development activity essential for representing open source health. The transparency of open source software development on platforms such as GitHub and GitLab make analysis and comparison of trace data to understand community health possible. However, individual project activity metrics do not provide a full view of community health. The measurement of open source community health is confounded because health metrics may have different meanings for different projects, and there is little consensus about the correct way to calculate metrics across projects. Additionally, open source metrics research is often discrete, conducted at a point in time and not focused on the specific needs of metric consumer communities like open source community managers and open source program offices. To get a full picture of open source community health, research and tooling needs to develop shared metrics definitions that can not only provide insight into a project's health, but also provide insight into software life cycles and ecosystems. This paper focuses on our 4-year engagement with the CHAOS project. So the CHAOS project is a Linux Foundation project focused on creating standardized community health metrics and open source software for analyzing community health. The project has 3 related software projects, Augur, Cregit, and Grimoire Lab. The project includes members from 70+ organizations such as Red Hat, VMware, Intel, Mozilla, the Eclipse Foundation, Oath, and Bitergia. The CHAOS project has 5 working groups with focuses on common metrics, project evolution, risk, value, and diversity, equity, and inclusion. And each of those working groups defines metrics associated with their focus area. To date, CHAOS has defined more than 50 community health metrics. Specifically, this paper presents some of our insights from the Augur project. This work is embedded within the CHAOS project and is based on interviews and engagement with open source stakeholders. Work with the Augur project is focused on providing software tooling that satisfies the needs of open source community managers and open source program offices. For example, our fieldwork identified that community managers want to be able to compare projects, identify trends, and understand contributor behavior. So Augur has 4 core design principles for making sense of data. These principles can be operationalized through 4 human-centered data science strategies. The first one being comparison. Comparison lets people navigate complex unknowns, as well as letting them see how their project compares with other projects. The second is trajectory. Trajectory makes time a fundamental dimension in all open source health indicators. The third is transparency. Transparency makes the provenance from raw data to open source health indicator visualization transparent, and provides traceability back to the CHAOS project where those metrics are defined. And then fourth is visualization. Enabling visualizations is downloadable, for example, as a CSV or a SVG or an other type of data exchange format, allows stakeholders to build local stories. So an Augur empowers open source community managers to tell data-driven stories. Augur is designed to enable the rapid, reflexive exploration of project health using CHAOS metrics to answer questions as they emerge from experience, and used to understand specific questions about health and sustainability within an organizational context. And this includes open source project ecosystems and corporations. So in our first example of using Augur to narrate project health, we explore the co-evolutionary nature of interdependent or related repositories. Here in this example, we have 2 Jupyter Hub repositories. One is the main repository, and the second is a fork that was created to scale Jupyter Hub through Kubernetes. What we can see through this this visualization of code changes and lines of code changed for the 2 projects is that the peaks and valleys of development activity seem to correspond. This may indicate work being done in the Jupyter Hub Kubernetes project is being contributed back to the original project. So in our next example, we can compare competitive projects. So here we compare the Zephyr project with an anonymized collection of potential competitors in the embedded operating system space. And we compare them on the basis of pull request merge success or pull request merge failure, in this case, accepted or rejected. This comparison may provide insight into how stable development activities are for all of these projects over a period of time. From this visualization, we can see that Zephyr's development activity appears to be pretty stable. And additionally, the project comparison shows similar numbers for merge success across all of the projects, but does indicate higher numbers of merge failure for several of these projects. So our last example explores second-time contributors to the SALT project over the course of a year. The comparison is made by in the project between quarters. So the comparison may inform how the project is growing or changing, and can provide deeper insight into how the project may be retaining new contributors. So many researchers are capable of doing this type of analysis on software repositories. However, there are few researchers and software tools that make a coordinated effort to develop reusable open source software health metrics around a range of concerns. So our hope is that by standardizing these metrics, by sharing our approach and our accomplishments to date, this work will inspire a discussion about how to make research software aimed at providing a coherent view of open source community health that is highly adaptable to changes and sustainable. So this is where we're at. Through our work with the CHAOS project, we've helped define more than 50 standardized health metrics. And our work with Augur has begun to enable open source stakeholders to create stories and narratives about open source health and sustainability. But this work is still emergent, and future work needs to continue standardizing health indicators through the definition and identification of metrics. And then additionally, we need to make these metrics widely available. So we also need to continue to work on tools that can look across projects and software ecosystems. Emerging work within the Augur project seeks to build a computational linguistic pipeline for the exploration of diversity, equity, and inclusion. Specifically, Augur is using a collection of 6 machine learning techniques to analyze message inclusivity. So including sentiment analysis, novelty, clustering, topic modeling, discourse analysis, and k-means clustering of activity level changes. If you're interested in knowing more about this emerging work, please reach out to Sean after the presentation. Thank you.